Good morning, all of you. Welcome to C. Jayendra Rank Zone. Now we are in lecture 3 of P block elements. Listen carefully, all of you. This is very important lecture. So in this lecture, we are going to discuss more about compounds, boron compounds. So let us start now. Yes. So next topic we have orthoboic acid, that is H3BO3. H3BO3 is an important mineral as boron is available. It is available in combined state as salts of boic acid. It is a white crystalline solid. It is having a soapy touch. It is sparingly soluble in cold water but highly soluble in hot water. So H3BO3 is highly soluble in hot water. So this is called boic acid and it is used as caramel powder. This already we discussed. So caramel powder it is used as caramel powder. It is also called as orthoboic acid. So how it is prepared, let us see now. An aqueous solution of boic acid is found to be weakly acidic in nature. H3BO3 is also a Lewis acid because of the presence of boron, which abstracts OH minus ion from water and leaves H plus ions to make the solution more acidic. So in solution form, it is existing as BOH taken 4 times minus plus H plus ions. This is existence of H plus due to the presence of H plus ions, it is weakly acidic. Next continuation. Preparation. So orthoboic acid is prepared by acidifying the acidifying aqueous solution of borax. So first borax, that is Na2B4O7 combined with HCl and water, it forms NaCl and BOH taken place, that is boron hydroxide. This Na2B4O7 combined with sulfuric acid and forms plus water, it forms sodium sulfate along with boic acid. So these are the two steps involved in the preparation. So first step, this is also same H3BO3 only, and this is also H3BO3. So it is prepared by acidifying an aqueous solution of borax. So borax is treated with dilute acids along with water. So there is solution, borax solution is taken along with HCl and H2SO4. It forms salt plus boic acid, that is H3BO3. H3BO3 can also be prepared by the hydrolysis of boron hydrides, halides and hydrides. So BCl3 on hydrolysis forms H3BO3 plus HCl and B2H6. This is called diboron. B2H6, the hydride of boron, is very important compound. So diboron combines with water and forms H3BO3 plus 6 water molecules. So boron hydrates, halides, and even with boron nitrates also it can be prepared boron nitride. So it is Bn plus H2O. It combines together to form BOH taken place along with ammonia gas. So BOH taken place is also nothing but hydroboic acid, that is boic acid plus ammonia gas. So it is prepared by the hydrolysis of boron halides and boron hydrates along with boron nitrides. One more equation I have added. So it is also prepared from nitrides. So boron nitride, it is Bn, combines with water and forms BOH taken place plus NH3, ammonia gas. So this is a preparation of orthoboic acid. And next it is also prepared from colomonite. So the structure of hydroboic acid. So third preparation I'll add up here so that it will be easy for you to identify. Third preparation, it is nothing but from colomonite. I'll write the spelling clearly. It is from colomonite. COLEMANATE. Colomonite. So it is prepared from colomonite. What is the formula of colomonite? It is calcium Ca2B6O11. This is called columenate mineral. This on reaction with sulfur dioxide along with water. This on reaction with sulfur dioxide plus 4 molecules of sulfur dioxide along with water plus 11 molecules of water molecules, 11 moles of water molecules. Together they combine to form calcium bisulfate, 2 moles of calcium bisulfate and CaHSO3 taken twice plus 6 moles of H3BO3. So these are the four preparations we have from boron nitrates also, as I told you. So boric acid can also be prepared by the hydrolysis of boron halides, boron hydrates, boron nitrates, and also from columenite. Columenite is Ca2B6O11. So finally poured columenite is dissolved in boiling water and sulfur dioxide is passed to the solution. Finally divided columenite is dissolved in boiling water. Boiling water is important here, and sulfur dioxide gas is passed through the solution, which results in the formation of boric acid and calcium bisulfate. Boric acid and calcium bisulfate. So please note down these three preparations of orthoboric acid. Now we are going to see the structure of orthoboric acid. Very, very important. So in H3BO3, the central atom boron undergoes what type of hybridization? It is sp2 hybridization. Due to the presence of hydrogen bonding, it is polymeric in structure. So sp2 hybridization forming planar BO3 3 minus units. These H3BO3 units involve in hydrogen bonding to give layered-like structure to H3BO3 as shown in the figure. So that is why it is polymeric structure due to the formation of layer. So why it is forming layers? Because of hydrogen bonding. You can see this is hydrogen bonding with other boron atom. This is hydrogen bonding. This is hydrogen bonding. This is also hydrogen bonding. So due to the presence of hydrogen bonding, it gives layered like structure, which gives rise to the polymeric. Polymeric means so many H3BO3 units combined together to form one single molecule. So it is called polymeric structure. So very important point is here sp2 hybridization. Central boron atom undergoes what hybridization? sp2 hybridization, and the wing is planar wings. We have planar wings like this, trigonal planar wings, and thus these H3BO3 units involved in hydrogen bonding to give layered structure to H3BO3 as shown in the figure. And this is polymeric structure of H3BO3. Very, very important. So in these important points I have written, so please make a note of it. Next, hydrides of boron, very, very important. Hydrates of boron. So these are the preparations of orthoboric acid, and now we are going to start hydrides of boron, which is very important. So boric acid behaves as strong gas in the presence of cis diols. So structure of boric acid we have done already. Next we have to start hydrates of boron. The binary compounds of boron. So the binary compounds of boron and hydrogen are known as boron hydrides. What are boron hydrides? The binary compounds. Binary compounds of hydrogen and boron are called boron hydrides. So it contains only boron as well as hydrogen only. So that's why they are called as boron hydrides. These are boron forms two types of hydrates of formula Bn Hn plus 4, first one, and second one Bn Hn plus 6, second series. So these series are called as nidoboens. Bn Hn plus 4 are called as nidoboens. They are called as nidoboens. Please note it down. And Bn Hn plus 6 are called as arachnoboens. Arachnoboens, the other name of these. So nidoboens and arachnoboens. So nidoboens, what we have, Bn Hn, the 6 types are also called as arachnoboens with web-like structure. And B4H10 nidoboen have nest-like open structure. They have nest-like open structure, and these have what? Web-like structures. So web-like structures. So examples, we have so many examples for nidoboens, and in the best example is B2H6. B2H6. That is nidoboen. First example, that is called as diboen. It starts with B2H6. Next, B5H9. So B5H9. So BNH B5H9, because Bn is 5 and 5 plus 4 9. This is called as pentaboen, diboen, and so on. Next we have B6H10, B6H10. So 6 plus 6 12 actually it should be. So B6H12 actually it should be hexaboen. B6H12 hexaboen. B6H12 we have hexaboens. These are all coming under nidoboens, hexaboen. B6H12, 6 plus 4 10. So B6H10 is also there. That is called as hexaboen. And this is B6H12 is also called hexaboen, in which it is coming under BnHN plus 6. So these are the types of boron hydrates. So binary compounds of hydrogen and boron are called as boron hydrates. It forms two types of hydrates. The general formula is BnHN plus 4. These are called as nidoboens. And BnHN plus 6 arachnoboens, and BnHN plus 6 types are called arachnoboens with web-like structure. These are having web-like structures. And B4H10 nidoboens have nest-like open structure. Nest means you know what is next. So it is nest-like open structure. So these are the two types of hydrates of boen. Let us see now. In this important is diboen only. So properties of diboen they have given. As I told you, we have syllabus up to diboen only. So that is B2H6. So diboen is what? B2H6. Preparation and properties. Let us start with properties of diboen. It is a colorless toxic gas. Toxic means poisonous with suffocating odor. Its boiling point is minus 93 degrees C. B2H6 readily catches fire when exposed to air. So when exposed to air, it catches fire. As the reaction is highly exothermic, it results in the formation of B2O3. B2O3 plus water plus 1976 kilojoules per mole. Lot of energy is released. Diboen readily hydrolyzed to form H3BO3. So as this reaction we have already seen in the preparation of H3BO3. So B2H6 on reaction with water, it forms H3BO3 plus 6H2. So B2H6 readily catches fire. So this action of heat, it readily catches fire and forms B2O3. And this reaction is highly exothermic in nature. Diboen is colorless toxic gas with a melting point of minus 93 degrees C. With the boiling point of minus 93 degrees C, and melting point is minus 165 degrees C. Still lower. And boiling point is 93 degrees C. It is highly reactive gas and must be handled with care. It catches fire spontaneously in the air, and the reaction is explosive in nature as a large amount of heat is produced. So it readily catches fire when exposed to air, as the reaction is highly exothermic. Next, diboen combines with water and forms orthoboic acid, that is H3BO3 directly. And reaction with alkalis, B2H6 combines with alkalis. One more reaction I'm adding, please note it down. It combines with alkalis, potassium hydroxide and sodium hydroxide, to produce metaboids along with water, to produce metaboids, that is 2NaBO2, that is metaboids plus 6 moles of hydrogen gas with the release of hydrogen gas. Very, very important reaction. So diboen combines sodium hydroxide or potassium hydroxide to form their respective metaboid, that is sodium metaboid or sodium boid, you can say sodium metaboid or potassium metaboid, that is KBO2. Potassium metaboid is what? KBO2 or KBO2. Next, continuation. Properties of diboen. Structure of diboen is most important. Diboen undergoes cleavage and forms addition products. It undergoes cleavage, breakup, and forms addition products when treated with Lewis bases. So it combines with carbon monoxide, combines with what? Carbon monoxide, and forms 2BH3.CO. B2H6 combines with nitrogen, trimethyl nitrogen, that is nothing but CH3 taken thrice N. This Me3 is nothing but CH3 taken thrice N and forms 2BH3 N Me3. So N trimethyl, addition product. Next, diboen combines with ammonia. The reaction of diboen with ammonia is very important. Diboen reacts with ammonia as Lewis base, but the product forms depend on the conditions. So B2H6 when combined with ammonia at low temperature, it forms an additional product that is called B2H6.NH3, that is addition product. And this is existing in the solution as BH2NH3 taken twice plus BH4 minus. So the direct product formed with ammonia is an ionic product and can be formulated as, so that's what diboron forms an ionic product. Here plus and minus cation and anion is formed. So the adduct formed with ammonia is an ionic product and can be formulated as BH2. This point is very important. Definitely they'll ask in the examination. So the adduct product formed with ammonia is an ionic product. It exists in solution as BH2NH3 taken twice plus into BH4 minus. So it is resulting of cation as well as anion. Next, very important with ammonia. With ammonia depends on the condition, it forms many compounds. So let us see what are the other compounds it forms. Yes, when adduct formed by B2H6 with ammonia is heated further to high temperatures, it forms a volatile compound called boazole or bozine. Very, very important. So B2H6 on combination with boazole on ammonia, it forms bozine. So 3 moles of B2H6 combine together to form B3NH6 plus hydrogen gas. This is called as inorganic benzene. So this bozine is also called as inorganic benzene as its structure resembles benzene ring with alternate BH and NH groups. Alternate BH and NH groups. So this is very, very important. So diboron when combines with ammonia, it forms an addition product. This addition product at high temperature with excess of ammonia, at high temperature it forms boazole or bozine. It is also called as inorganic benzene because its structure represents ring structure like with alternate BH and NH bonds, BH bonds and NH groups. So the formula of inorganic benzene is B3N3H6. Let us see the structure of this if it is given. Otherwise, I'll draw it now. So it is called inorganic benzene. The structure of diboron. Before this structure of diboron, I'll give the inorganic benzene structure. So please note it down because it is not given in the PPTs. So this is called inorganic benzene with the 3 BH-NH bonds. So let us write the structure of inorganic benzene. I'll try to write it properly. B3N3H6. So first nitrogen, this combined with boron. Second again nitrogen, this combined with boron. Third again with nitrogen, alternate NBN with the boron, and finally boron, nitrogen. So it has alternate double bonds. Alternate double bond means first, second, and third. So in each unit it consists of BH, NH, BH, NH, BH, NH. So this is called what? Inorganic benzene. It represents benzene because it contains alternate double bonds. So it is called as inorganic benzene with 3 BH and NH groups. BH 3 BH and 3 NH groups. Alternate double bonds with alternate double bonds with alternate double bonds. So please make a note of this. It is very, very important. So it forms 3 BH NH groups with alternate double bonds. So this is called inorganic benzene. This is called what? Inorganic benzene. This inorganic benzene on reaction with bromine. This inorganic benzene on reaction with bromine at very low temperature, that is 0 degrees C, it forms additional compound called, so all the double bonds will be removed and replaced with single bonds, and it forms tribromo-bozine, N-tribromo-bozine. So it is called tribromo, results in the formation of all, here total 6 BRs will be added to this. So it forms B3N3H6 BR6. What this forms? It forms B3N3H6 BR6. With each double bond and nitrogen, it forms bromine will be added up. So it forms B tribomoborazine or N tribomoborazine. So it forms B, that is boron tribomoborazine, and nitrogen tribomoborazine. Nitrogen tribomoborazine. As I told you, each bromine is added to, total 6 bromines are added to 3 nitrogens and 3 bromines. That's why it is tribomobromazine and N-tribomoborazine. So total the compound and the formula of this compound is B3N3H6Br6. B3N3H6Br6. Very, very important. So this on reaction. So borazine on reaction with 3 moles of bromine molecule, it forms what? B tribomoborazine, N tribomoborazine. And this diboene also, this is inorganic benzene combines with water. Combines with water, 3 moles of water. On hydrolysis, it forms OH taken twice. OH taken twice, B3N3H6, B3N3H6, B3N3H6 plus hydrogen gas, 3 moles of hydrogen gas. So these are the reactions. 2 reactions are given for borazine. It is more than enough. So please make a note. This is not there in the PPT. It will be clear. So that's why I request you to write down in your classwork. This is the structure of inorganic benzene as it resembles benzene-like structure. So that's why it is also called as inorganic benzene. It contains 3 BH and 3 NH groups and with alternate double bonds. And this inorganic benzene on reaction with bromine, it forms boron tribomoborazine along with nitrogen tribomoborazine because 6 borons will be added to 3 nitrogens and 3 borons. That's why tri. And this inorganic benzene on hydrolysis forms an addition product called, this on hydrolysis. Borazine gets slowly hydrolyzed to water to produce hydrogen gas, boic acid, and ammonia. So it produces hydrogen gas, boic acid, and ammonia. Under controlled conditions, hydrolysis yields BOH3, BOH taken as B3 and 3H6 addition product. So, and this on hydrolysis again, hydrolysis with 9 water molecules, it forms controlled hydrolysis, it forms this, and normal hydrolysis, it forms 3 moles of ammonia plus 3 moles of orthoboic acid plus 3 moles of hydrogen gas. So it forms orthoboic acid, ammonia, and hydrogen gas on hydrolysis. So inorganic benzene on hydrolysis forms ammonia, orthoboic acid, and hydrogen gas. Inorganic benzene on reaction with bromine forms addition reaction. Inorganic benzene under controlled hydrolysis will form OH taken as B3N3H6 along with hydrogen gas. So these are the 3 reactions of inorganic benzene. All are important. That's why I have written here. It is not there in the PPT. So please make a note in your classwork because I am going to clear this. It will not be added in the PPT. So please make a note of this. Next continuation. Now we'll go with structure of diboene. This is also very important. From this they'll ask one question. Definitely. What is the structure of diboene? How many bonds it contains? So let us start now. Diboene has 2 bridging hydrogen atoms. It has how many bridging hydrogen atoms? 2 bridging hydrogen atoms between 2 boron atoms that form 3 center 2 electron bond. 3 center 2 electron bond is also called as banana bond or tower bond. So it is also called as banana bond or tower bond because it contains, so this is boron and this is boron, so it contains 2 hydrogen bridge atoms. So these 2 are called hydrogen bridge atoms, and this boron will combine with 2 hydrogens. This boron will combine with 2 hydrogens. So this is the structure of diboene. Simple it is. So 3 centered 2 electron bond. 3 centered 2 electron. This is 1, 2, 3. 3 centered 2 electron. 1, 2, 3. 3 centered 2 electron. So it contains 3 centered 2 electrons. What is 3 centered means? First, second, third, and 2 electrons. For this, first, second, third, and 2 electrons. So this is what it is called 3 centered 2 electron bond. The 4 terminal bonds. These are called terminal bonds. These are called what? 4 terminal BH bonds lie in one plane, which is regular 2 center 2 electron bonds. Very important. 2 center 2 electron bonds. 2 center 2 electron bonds. The four terminal BH bonds lie in one plane. This is outer terminal hydrogen bonds. These are called terminal hydrogens. These two are bridge hydrogens. It has four terminal hydrogens, two bridge hydrogens. So please listen carefully. One, two, three, four. These four terminal hydrogens and two bridge hydrogens. These four terminal BH bonds lie in one plane. They are lying in only one plane, which is regular two center, two electron bonds. And the two bridging hydrogens are present above and below the plane containing the four terminal hydrogen bonds. So it is lying above and below the plane. So these two bridging hydrogens are present above and below the plane containing four terminal hydrogens. So this is the structure of diboron. Very, very important. It contains three center, two electron bond. And on the whole, it contains three center, two electron bond. And the terminal pH bonds lie in one plane, which is regular two center, two electron bonds. And in this, the boron undergoes sp3 hybridization. What hybridization? It undergoes sp3 hybridization. So this is the structure. So 1, 2, 3, 4. So this is called 1, 2, 3, 1, 2, 3. So here, if you see the structure carefully, you will get like this. Two boron atoms will be present like this, and these two boron atoms are linked by means of hydrogen, and these two boron atoms are linked by means of hydrogen, and these two borons are called terminal hydrogens. For these two hydrogens are also called as terminal hydrogens, and these two hydrogens lie above and below. By this is they are lying in the same plane. These four hydrogen atoms lying in the same plane. These four hydrogen atoms lying in the same plane, and these bridging hydrogen atoms lie above and below the plane. And each in diboron in B2H6 boron undergoes sp3 hybridization. What hybridization? sp3 hybridization. It is called open book-like structure. What is it called? It is also called as open book-like structure, or you can say three center two electron bond or tower bond. Very, very important point. So please note it down. Next continuation. So diboron reacts with metal hydrides to form corresponding tetrahydroborates known as borohydrates, that is lithium boron hydrate and sodium boron hydrate are good reducing agents in organic synthesis. So they readily combines, the diboron readily combines with metal hydrides. Diboron readily combines with metal hydrides and forms, diboron readily combines with metal hydrides and forms, what does it forms? They form lithium BH4, that is LiBH4. It is also called as tetrahydroborates, and so on. So that is the property of diboron. So diboron readily combines with metal hydrides. They readily combines with metal hydrides and forms the compound LiBH4 and NaBH4. They are used as good reducing agents in organic synthesis. In organic synthesis, they are readily formed. So if you want, you can write one equation here I'm writing. So B2H6 combined with sodium hydroxide, sorry, sodium hydrate, metal hydrate, and forms NaBH4 and forms what? NaBH4 plus hydrogen gas. So NaBH4, Na plus BH4 minus. This is an ionic compound. Na plus and BH4 minus. It's an ionic compound. So boron compounds usually covalent, but certain boron compounds are ionic in nature. So this is an ionic compound. With lithium also it forms the same. With lithium also, lithium hydride, it forms the same. So it's very, very important. So diboron combines with these complex borohydrates. This is called complex borohydrates. We can write in complex like this. So these complex borohydrates are used as reducing agents in organic synthesis, in organic compounds, in the synthesis of organic compounds. So it is very, very important. Please make a note. Next continuation. So from diboron, you'll get many questions. That's why it's very, very important, as I told you. Next, use of boron and aluminum. Now we have boron fibers, which are hard and light, are used in making bulletproof jackets and aircraft. So the fibers of boron, which are hard and light, are used in making bulletproof vests, that is jackets and aircraft. Boron nitride is hard as graphite and used as abrasive. Boron 10 is a neutron absorber and also used as protective shields and control rods in nuclear chemistry. So even B10 rods is a neutron absorber. So in the nuclear reactor, the fast moving electrons can be slowed down by absorbing neutrons. Fast moving neutrons can be absorbed by B10, can be absorbed by B10, isotope of boron. B10 is isotope of boron, which controls chain reaction, which controls chain reaction. So nuclear fission chain reaction is being stopped by observing the fast moving neutrons. So fast moving neutrons can be absorbed by B10 isotope. This is isotope of boron. Actually B11 is present. So B10, the isotope of boron, is used for observing fast moving neutrons in nuclear chemistry. In making heat resistant glass apparatus is also used in making heat resistant glass apparatus, means that can withstand high heat of temperature. Next, dilute solution of boic acid is used as mild antiseptic. Dilute solution of boic acid is used as mild antiseptic. Aluminium forms alloy with copper, magnesium, manganese, silicon, and zinc, which are extensively used in aircrafts. Aluminum is used in making utensils. You know, pressure cookers are made up of aluminum only, packaging industry, etc. So this pressure cooker, which you are using for domestic purpose, it is made up of aluminum. Pressure cookers usually they are made up of aluminum, and even we have aluminum foils for storing of book, aluminum foils for food storage, food packets, because it remains the things hot. Next continuation. Let us see some questions now. H3BO3 has slippery nature due to weak van der Waals forces between interlayer planes. It acts as monobasic act. The presence of banana bonds within the layer make it planar like graphite. The presence of hydrogen bonds between the layers. So definitely it is the presence of hydrogen bonds. That's why it is used in carom board. So it has slippery nature due to formation of layer-like structures between the layers. The presence of hydrogen bonds. So answer is D. So it is containing weak van der Waals. So it is slippery nature. Slippery means not soft. So answer is correct only. That is van der Waals force only. Weak van der Waals force between interlayer planes. I thought it is slippery nature means it is soft. It is soft in nature due to the presence of hydrogen bonds. So this is making up soft nature. That's why it is used in carom board. Carom board. Next continuation. When boic acid reacts with aqueous NaOH, boic acid means H3NO3. So it combines, it is basic in nature. So it is acidic in nature. It combines with base, that is sodium hydroxide. It forms a salt. The salt is produces what? NaBaOH taken 4 times NaBO3. So easily you can tell the answer because this reaction is already we have studied. It is nothing but NaBH taken 4 times. NaBOH taken 4 times result in the formation of salt. Next continuation. Diboron has all boons with sp3 hybridization, two sp3 sp3 sigma bonds, two centered 3 electron bonds, all the above. So answer is it contains, as I told you, it is undergoing sp3 hybridization. It contains two sp3 sigma bonds, and it contains two centered 2 electron bonds. Two. How many? Two, three centered. You listen carefully. This is two, three centered, 2 electron bonds. Why? Because one is BH, BH, BH. These are terminal hydrogens. This is called bridging hydrogen. Another is again BH, BH, and these two are again BH. So this is BH. So it is nothing but two three centered, one three centered, two three centered, 2 electron bonds, 2 electron bonds. So it is two three centered, 2 electron bonds. It is sp3 hybridization. Both the boron atoms, each boron undergoes sp3 hybridization. sp3 sp3 sigma bonds. All borons with sp3 hybridization. So all are correct. So answer is what? All the above. Very, very important. This question will give you maximum information about structure of diboron. So this question is very, very important. Please make a note of this question. It has all borons with sp3 hybridization, two borons undergoing sp3 hybridization. It has two sp3 sp3 sigma bonds. It has two three-center 2 electron bonds. Two three-center 2 electron bonds, also called as banana bond or tower bond. Also called as banana bond or tower bond. Tower bond. So this is the structure of diboron, very important. As I told you, based on structure of diboron, definitely you'll get question. Next, consider the following statements for diboron. Boron is approximately sp3 hybridized. BHP bond angle is 180 degrees. There are two terminal BH bonds for each carbon boron atom. There are only 12 bonding electrons available. So total there are only 12 bonding electrons available. So which is the right option? You can just see here. Of these statements, first statement, second, third, and fourth are correct. 1, 2, 3 are correct. 2, 3, 4, and answer is 1, 3, 4 are correct. What is the first statement? It is sp3 hybridization. Third statement. What is third statement? Let us move back. So third statement and fourth statement. You can see here. So third statement and fourth statement are correct. Very, very important questions. Next. So now we are going to discuss some additional points in this concept, that is preparation of diboron, and we have done about boron compounds. So I'm sharing whiteboard to you so that it will be easy to write, and that whiteboard we can save it. So that's why I'm writing here. So additional points with respect to borazine, diboron, etc. Now we are going to discuss questions also. So bond angle is 180 degrees is wrong. Bond angle is 180 degrees is wrong for diboron. Now we are going to start structure of bonding and borazine. So now we are going to discuss MCQs based on boron only. MCQs based on boron. Very, very important. Please note it down. Only boron questions are right based on boron compounds. So all the MCQs are very important. Please make a note. Question number 1. Let us start. So these are the important boron compounds. Now we'll start with MCQs based on boron compounds. B. Only boron I will start. So that in next session we'll do about aluminium. First question. H3BO3 is option A, monobasic and weak Lewis acid. Option B, it is monobasic. Monobasic means it is only one H plus ions, and strong Lewis acid. Strong Lewis acid. Option C, it is monobasic and weak Bronsted acid. Monobasic and weak Bronsted acid. And fourth one, it is tribasic and weak Bronsted acid. Weak Bronsted acid. So these are the 4 points we have. So the right answer, you already know that H3BO3 in aqueous solution, it changes to BOH plus H plus ions. So BOH taken twice and H plus ions. So that's why it is actually BOH taken twice and H plus ions. So that's why it is weakly basic and strong Lewis acid. So it is minus and H plus. So it is monobasic and weak Lewis acid, because it is giving only one H plus ions. It is called monobasic, and it is a weak Lewis acid. Weak Lewis acid. So this is the solution. Next question. Question number 2. Only boron compounds I'm discussing questions, very, very important questions. Please note it down. Three-centered two electron bond is present in three-centered two electron bond is present in option A, it is B2H6. Option B, it is BCl3. Option C, it is Al2Cl6. And option D, it is ammonia. So straight away we can say blindly two-centered three electron bond is present in dipoene. So answer is B2H6. It contains three-centered two electron bond. Next question number 3. Just now I explained, that's why I'm not writing the answer solution properly. You can understand that. Next question number 3. BCl3. This question is very, very important. BCl3, that is boron trichloride, does not exist as dimer, but BH3, but boron hydride exists as dimer because this everyone should get doubt why B2H6 is existing, but why not B2Cl6. Chlorine is more electronegative. Chlorine is more electronegative. That's first reason they have given. Chlorine is more electronegative. Chlorine is more electronegative, does not fit. More electronegative than hydrogen. Option 1. Option B, large size of chlorine atom. Large size of chlorine atom does not fit between small sized boron atoms. Small sized boron atoms, while small sized hydrogen atoms can fit between boron atoms, This is option 3. Sorry, option C. Now we are going to write. There is p-pi back bonding. P-pi back bonding in BCl3. Back bonding in BCl3 is present. That's why it is not forming dimer. Option D. Both B and C. Both B and C. Very, very important. So first, anyway, chlorine is more electronegative than hydrogen. It is correct only, but here it is not the reason. So second one, large size of chlorine atoms. Large size of chlorine atoms does not fit between small sized boron atoms, while small sized hydrogen atoms can fit between two boron atoms. This is absolutely right. And this is also there. P-pi back bonding is present in BCl3 as we already discussed in the previous lecture. So P-pi back bonding is present in halides of boron. So answer is option D, that is both B and C. Very, very important this question. So why BCl3 does not exist as dimer, whereas BH3 exists as dimer? Due to small sized hydrogen atoms that can fit between two boron atoms, whereas large size of chlorine atom does not fit between two small sized boron atoms. And moreover, p-pi back bonding takes place in BCl3. This back bonding I explained in the previous lecture, so you can see clearly. Next question. So from this chapter, definitely you'll get questions based on boron compounds. So I want to discuss almost all the boron compounds. That's why these questions are very important. So please discuss. So please listen carefully now. We are going to complete this boron now. The color of ferric metabolite is The color of ferric metabolite is option A is nothing but the color of ferric metabolite is yellow, blue. Option A it is yellow. Option B it is blue. Option C it is green. And option D it is gray color. So straight away you can say it is green color due to the formation of is nothing but what? It is green color, that is borax bead test. You can refer borax bead test which we have discussed in the previous lecture. So it forms ferric metabolite, that is FeBO2 taken twice, which is green in color. It is green in color. Next continuation. Question number 4. Next question. Boron has boron has an extremely high melting point and extremely high melting point because of due to option A it is allotropy, option B it is its ionic crystal structure, ionic crystal structure due to its ionic crystal structure, ionic, this is ionic crystal structure. Option C it is strong van der Waals forces between its atom, strong van der Waals forces, strong van der Waals forces between its atom. And option D it is strong binding forces in the covalent polymer, strong binding forces, strong binding forces in the covalent polymer. So answer, why this boron has high melting point? Because of allotropy, first reason. Second reason is its ionic structure, ionic crystal structure. Third reason is strong van der Waals forces between its atom. And fourth reason, strong binding forces in the covalent polymer. So answer is fourth option, that is strong binding forces in the covalent polymer. So these are the important questions from boron compounds. Next we'll go for question number 5. Question number 5 now we are going to write. This is previous questions. BOH3, that is hydroboric acid, that is H3BO3 plus NaOH is base. It forms reversible reaction. It forms metabolite, that is sodium metabolite plus NaBOH taken 4 times plus H2O. Plus H2O. This is the reaction. How can this reaction, this is previous IIT 2005 question, so advanced question, how can this reaction can be made to proceed in the Forward direction means we want only the products. Forward direction. So by applying Kp and Kc like forward direction. So by applying Lee-Chatter's principle, which we have completed in chemical equilibrium. Option A, by the addition of 6, by the addition of cis 1 comma 2 diol. Option B, by the addition of borax, by the addition of borax. Next, by the addition of trans 1 comma 2 diol, and fourth one by the addition of sodium hydrogen phosphate, by the addition of NaH2PO4, sorry, Na2HPO4, Na2 Na2HPO4, that is disodium biphosphate. So this question is very important. This has come from 2006 IIT advanced question. So it is the answer for this question we are going to discuss now. So by the addition of what? By applying Lee-Chatter's principle you can do. So this question very, very important. Please make a note. So the answer for this is by the addition of cis 1 comma 2 diol. By the addition of cis 1 comma 2 diol, I will complete the equation. Please make a note. By the addition of cis 1 comma 2 diol, answer. So this is previous JEE mains question, JEE advanced question, not even JEE mains. It is JEE advanced question. So please make a note of it. So I'll write the equation now. Solution. So answer is by the addition of cis 1 comma 2 diol. So this reaction is reversible. Hint I am giving. This reaction is reversible due to the hydrolysis of sodium metabolite. So in the presence of complexing agents, in the presence of complexing agents, in the presence of complexing agents, such as cis 1 comma 2 diol, comma, glycerol, etc. Glycerol, that is CH2OH, CH2OH, etc. A complex is formed and prevents hydrolysis. A complex is formed. A complex is formed which prevents hydrolysis of NaBO2, which prevents hydrolysis, that is backward reaction. Hydrolysis of, which prevents the hydrolysis of NaBO2, because backward reaction is what? NaBO2 hydrolysis. So by the addition of cis 1 comma 2 diol or glycerol or catechol, etc., a complex is formed which prevents the hydrolysis of NaBO2. So backward reaction can be prevented by adding a suitable complexing agent. Suitable complexing agent. This question is very, very important. It has come for IIT Advanced 2005 question. So that's why it is very, very important. Please make a note of it. Next question. Question number 6. Question number 6. Very, very important. This question also. Diboane is prepared on large scale. Diboane is prepared on a large scale. Diboane is prepared on a large scale. Diboane is prepared on a large scale by option A, BF3, reaction between BF3 and 6LiH, that is 2BF3 plus 6LiH. They have given all the reactions at 450 kelvins to form V2H6 plus 6LiF, V2H6 plus 6 molecules of lithium fluoride. Option B, BCl3, 2 moles of BCl3 plus 6 LiH, that is at same temperature it forms B2H6 plus 6 moles of LiCl, lithium chloride. Third option, BF3, on reaction with sodium hydride, 6 moles of sodium hydride, it forms B2H6 plus 6 NaF, that is sodium fluoride. Next, option D, 2 BCl3 plus 6 NaH, it forms B2H6 plus 6 moles of NaCl. So these are the options we have. So this is question number 6. Diboron is prepared on large scale at the same temperature. So they have given the same temperature is also same, that is 450 kelvins. So it can be prepared by a large scale by the action of boron trifluoride on lithium hydride. By the action of boron trifluoride on lithium hydride. So answer is first option. Next question. Question number 7. Borax bead test. Borax bead test is not given by all these questions we are discussing only boron compounds. Very, very important. That's why please make a note. A, copper salts. B, aluminum oxide, sorry, magnesium salts, cobalt salts, sorry. It is aluminum salts, option B, aluminum salts. Option C, it is nickel salts. And option D, it is cobalt salts. Cobalt salts. So borax bead test is not given for aluminum salts because for copper it is blue color, for nickel and cobalt it is green color or whatever color it is. For nickel and cobalt it is giving, for copper also it is giving, except, so answer is aluminum salts. Aluminum salts does not give response to borax bead test. Very, very important. Next question. So they can ask many questions from this chapter. I'm expecting question from boron compounds and total B. So that's why it's very important to discuss as many questions as possible. Next question. Which of the following is not an electron deficient compound? Which of the following is not an electron deficient compound? Which of the following is not an electron deficient compound? Option A, it is BCl3. Option B, it is AlCl3. Option C, it is B2H6. And option D, it is Al2Cl6. So we know diboron is also electron deficient compound, BCl3 is electron deficient compound, AlCl3 is electron deficient compound, and Al2Cl6 is not an electron deficient compound. Al2Cl6 is not an electron deficient compound. Very, very important question. Next, question number 9. Question number 9. So previous advanced questions I am discussing now based on this. Next question. Which of the following are incorrect statements? Which of the following are incorrect statements? Incorrect statements. Option A, BH3 is a stable compound. BH3 is a stable compound. It is more than one correct question, more than one correct option. Please make it note. It is more than one correct option. Option B, it is boron hydrides are readily hydrolyzed. Boron hydrides are readily hydrolyzed. Readily hydrolyzed. Option C, boron hydrides are formed. These hydrides are formed by the reaction of magnesium bromide. Sorry, by the reaction of Mg3b2 and dilute HCl. Next, option D, all BH bonds in B2H6 are equal. All BH bonds in B2H6 are equal. So we have to identify the incorrect statements in this question. Incorrect statements. So please make a note. It's very, very important. Incorrect statements. So first option BH3 is a stable compound is wrong because it is, I'm doing with blue pen. BH3 is a stable compound is wrong. Boron hydrides are readily hydrolyzed is correct only. They are formed by the reaction of Mg3b2 and dilute HCl, which is also correct. And all BH bonds in B2H6 are equal. This is wrong. So it is option A and D are wrong statements. Option A and D are wrong statements. So like these questions are expected, definitely. Next, last question for this lecture I'm discussing now. After that, we'll end up this session. And in the coming session, we'll discuss about some more points. Next question, select the correct statements. Select the correct statements. About B2H6, that is diboron. Option 1, B2H6 has three-centered two-electron bond. Three-centered two-electron bond. Option B, each boron atom has sp3 hybridized. Is sp3 hybridized. Next, option C, Hb dot dot B dot dot Hb bond angle is 122 degrees. Option D, all hydrogens in B2H6, all hydrogens in B2H6 lie in the same plane. So this is wrong option. Lie in the same plane. So because the bridging hydrogens will be above or below the same plane. So only 4 hydrogen atoms lie in the same plane. That is, terminal hydrogen atoms lie in the same plane. So now the right answer for this, it is more than one correct option. This is also previous advanced question. So the right option for this is A, B, C. Correct statements are, it has three-centered two-electron bonds. Each boron atom has sp3 hybridized. This is also correct. And Hb bond angle is 120 degrees. And this is wrong because only terminal hydrogens lie in same plane. Terminal hydrogens, terminal means outside, lie in same plane. lie in the same plane. But bridging hydrogens lie above or below. Bridging hydrogens, that is two hydrogen atoms, bridging hydrogen atoms lie above and below the plane. So this is the right statement instead of fourth statement. So like these questions are very, very important. So we have discussed maximum questions, most important questions of boron compound. So with this, I'm ending this session. In the next session, we'll discuss with some more topic. Thank you all.